So I'm going to start them. So hi everyone, my name is Danielle and I'm a PhD student at Diego Portales University. And it's a pleasure to be here today to talk about the accreted galaxy and an overview of TESS metal-pure accreted star candidates. So very first, we have evidence for many years now that the Milky Way was formed with contribution of accretion events and merger events. And one of the evidences that we have for this, the fact that our galaxy has stars with prograde and retrograde motions. So this basically means that while the majority of the stars in the Milky Way are moving in one direction, we have stars that are moving in the opposite direction. And it's very hard to explain why stars born in situ without any external influence would have such different motions. So we believe that the retrograde stars are part of the accreted component of our galaxy. So even though we have evidence for many years now that the Milky Way has different building blocks, now with Gaia mission, it was possible to recover information about these building blocks and to define different accreted galaxies. And what Gaia mission helped us to understand is how diverse the Milky Way is. So basically, if you see here in figure 1, we have the Sturmer diagram from Koppelman collaborators 2019, where basically the stars here in black are stars from the Milky Way, so stars likely born in situ, while each one of these groups of stars with different colors represents stars that might have a different progenitor. So this basically illustrates how the Milky Way is this beautiful mosaic of different stellar populations with different origins. So the main question that we approach here in this work that I'm showing today is what can these accreted stars tell us about the physical processes that led to the Milky Way as we know it today? So in order to approach this question, I would say that when we are studying the accreted past of the Milky Way through its stars, we have three main ingredients. So the very first ingredient is the dynamics, because with dynamics, we can understand migration of stars, we can identify stars that have similar motions, and therefore they might come from from the same progenitor. And this is something that Gaia is being completely fundamental in the last years for us to calculate. We also have the chemical abundances that are also very important, because from the chemical abundance we can understand the birthplace of stars and again explore the different building blocks of the Milky Way and the connection and histories of different stars. And finally, we have the third ingredient that are the ages. So with the ages, what we can do is basically put everything that we learned from the dynamics and chemistry and the physical process of our galaxy in a timeline, which help us to understand the evolution of the Milky Way. So in order to do this research about accreted star candidates, we use the TESS CVC sample, or the TESS CVC catalog, which is basically a catalog of very good data observed by TESS. And the TESS CVC catalog was also explored in Makarev and collaborators 2021, where the authors were able to calculate nu max and delta nu for thousands of stars and also ages for hundreds of stars. And our idea in this work is to explore the retrograde stars present in both Makarev and collaborators and TESS CVC catalog, which means that we would be exploring metal-pure TESS stars, because if you see here in figure 2 reproduced from Makarev and collaborators 2021, when they are giving us ages in that work, usually they are working in a higher metallicity regime than we would be working here with retrograde stars. So even though for the stars that we are working here, we didn't have like ages, we did have nu max and delta nu, which could help us to calculate the ages of the stars. So basically what we had for these would be 30 spectra for 30 stars. The spectra is high resolution and high signal to noise. Because these stars are not in any spectroscopy surveys, so they are not in apogee, they are not in Gala. So in order to have chemical abundances, we observe them with MIC spectrograph at Las Campanas Observatory, which is a very interesting instrument because it gives us a wider wavelength range than usually we have in spectroscopy surveys. And also it gives us the possibility to work with many many lines of different chemical elements. So the very first ingredient and the very first result that I would like to comment here is the dynamics. So basically, when we're working with accreted star candidates, it's very, very hard to differentiate the different progenitors. So it's very hard to attribute one star to a different progenitor. But we do have works in the literature that try to put the different building blocks of the Milky Way in the angular momentum energy space. So here in figure 4, I show you our results in terms of the angular momentum and energy. And what we observed is that the majority of our stars here are concentrated in a region that is attributed usually in the literature for Gaia-Enceladus stars. So Gaia-Enceladus were already mentioned in the previous talk, but very quickly, Gaia-Enceladus is one of the building blocks of the Milky Way, and likely the last major merger that the Milky Way experienced in the past was with Gaia-Enceladus. And in our case, the majority of stars have energy and angular momentum compatible of other Gaia-Enceladus stars. And another evidence that we have that these stars might be from Gaia-Enceladus is the fact that our stars also have high eccentricity. So here the stars are color-coded according to eccentricity, and you can see that the majority of our sample of stars also have eccentricities higher than 0.7. So the second result or ingredient that I would like to mention here are the chemical abundances. So the chemical abundances, here I'm showing in figure 5, the chemical abundance for 16 chemical elements. So I think the very first thing that we see here is that first, our results are going towards a lower metallicity regime from the reference article. So if you see here, the stars that we worked in this work are the magenta stars, while the stars from Makarev and collaborators are these gray stars. And basically the abundances from the in situ stars from Makarev and also the abundances of these gray stars here comes from apogee. So the other thing that we also see is that even though our sample has mostly metal poor stars, we do have some stars with a higher metallicity than we would expect for accreted stars that is usually minus 0.8 or minus 1. We also see that the stars here are in general alpha-rich stars. So these might reflect two things. The first thing that these stars might be old objects, and the second thing is that the progenitor of this galaxy might have a high star formation rate. What agree with what we know from Gaia-Enceladus. The stars are also rich in europium. So you can see that distribution of europium in general is going to be around 0.7x. So likely our processes were very important in the environment that these stars were born. Finally, the stars are copper poor. As you can see, when we are comparing them with the in situ population, they in general are lower in copper. And finally, something that is interesting is the fact that while when we are talking about the infrared, the accreted stars in general are considered to have low aluminum abundances, this is not what we observe here. So in the case of our optical data, what we get is that the stars are in general not aluminum poor. Finally, the last result or the last ingredient in our case was the ages, as I'm showing here in figure 6. So something very, very interesting that we find is that the ages have a range. So we have both old and young ages, stars, sorry. And this is quite interesting because when we are talking about Gaia-Enceladus, usually we have ages higher than 8 giga years. And another thing that we can see in this diagram is the fact that these stars that appear to be a little bit richer in the metallicity, they tend to be a little bit younger. So this is interesting because it's not the first time that this is reported in the literature. So earlier this year, we published this paper about this star that was first thought to be ejected from the central black hole of the Milky Way. But then using Gaia EDR3 data, so new Gaia data, and also chemical abundances, we concluded that this star would likely be an accreted blue straggler that was ejected from the central black hole of the Milky Way. So basically for this other star that we studied earlier this year, we again have information about the orbits, the abundances, and the ages of these stars. So using Gaia data, we were able to see that this star had retrograde motions, high eccentric orbits. That was something different from the previous works of the literature. Also that this star was rich in europium, what is something quite interesting because other works in the literature studying accreted stars. And in particular, stars from Gaia-Enceladus found that these stars might be enhanced in europium. But another thing that is quite interesting about that star was that using a different analysis than we did in this work, we find that star had an age of around 4.5 giga year, but this didn't agree well with the chemical abundances. So the chemical abundances show that this star was alpha-rich metal-poor stars. So what we thought was that why this star has chemical abundances that is compatible with old stars, but has an age of a younger star. So something that we thought is that this star could likely have experienced binary revolution and accreted mass from a companion in the past, and that is why when we are trying to measure its age today, it would show a younger age because it would be more massive than it initially was. So maybe this could be one hypothesis for our ages. So our ages are still a work in progress. So these results are preliminary. But if we have these young ages, it might be that we have again stars that have experienced binary evolution in the past, and um, and now we have different ages because of the accreted mass. So my conclusions. So basically, metal poor test stars represent an excellent opportunity to study the merger history of the Milky Way. Here in this work, we studied 30 metal poor test stars with retrograde and high eccentric orbits, which was only possible because of Gaia data. We also found a population of stars that are rich in europium. We found a range of ages in terms of our stars. So we have stars with the stars that are both young and other stars that are also old. And this is still a work in progress. We have many exciting questions still to be answered. Gaia is certainly going to help us a lot in answering this question. So Gaia has been fundamental in this work that I'm presenting to you, the previous work that we also published earlier this year. So Gaia EDR3 is coming, so likely we are going to have lots of other works about this topic. So thank you very much for hearing.
Yeah, thank you very much for your presentation, and let's move to the questions. Do we have questions from the audience? I think we should. Yes, please.
It is Emilio Alfaro, and my question is about the precision in dating the stars. You know, what kind of uncertainty or precision do you have for the whole?
Yeah. So basically, our ages are always below 1 gigayear. So actually, we have two stars with a precision of 2 gigayears, but usually the point about the stars being young is that the ages, if you consider the uncertainties of the ages, it's not enough to have a scenario where these stars are old. So actually, in the literature now, we have this young alpha-rich stars. There are basically these cases where when we have the chemical abundances, the stars are going to look old considering the chemical pattern, but the ages appear young. But in various work in the literature so far, people have uncertainties, but the uncertainties are not enough to consider that the stars could be old and are appearing young just because of the uncertainties. So our case is the same. So usually the uncertainties, except for two stars that have uncertainties of 2 gigayears, are below 1 gigayear. So even considering the uncertainties, the case of these stars that appear to be younger, it's not enough to a scenario where these stars would be old enough to be, I don't know, like above 8 gigayears.
Thank you.
There was another question. I think Carmen, you had a question.
This is Karma. Thanks for the talk. I would like to ask about these 30 metal poor stars. How were they selected? Perhaps you said, but I missed. And I was wondering if it is a subset of a large sample that you are studying, and if you have expectations of finding more Europe rich population among a larger sample.
Yeah, so basically about the selection, our idea here, because when we are talking about selection of accreted stars, we have people selecting them very differently. So we have people that does the selection only using dynamics, people that make selections using chemical abundances, and people that combine both things. In our case, we only selected the stars to be retrograde and to be present in TESS because our idea was to check these retrograde stars, see if they had evidence that they could really be accreted stars, and then use the seismic information to calculate the ages. But in our case, we basically select the stars to be retrograde, And then we double check it to see if they have other properties that would support the idea that they were accreted. Because in our case, because these stars weren't present in spectroscopy surveys, we didn't have, for example, chemical abundances to refine our selection. So we just selected stars that are that have retrograde motions. And sorry, what was the second question?
If you have a larger sample to study, it is all the stars that you have you present to study, or there are more that gives you expectation of finding more anomalous abundances.
Yeah, basically, I kind of have a lot of spectra of likely accreted stars in general for my PhD. So for this sample about like the TESS, the stars that are present in the TESS CBZ stars, we only have these study objects. But in terms of accreted stars that we could also find anomalous objects and anomalous age, we do have more stars selected differently. So we have selections that have that were stars that were selected according to chemical abundances, stars that were dynamics, stars that we selected using both things. So we have different samples of accreted stars that we can use to calculate chemical abundances, dynamics, and finally the ages. So maybe in the future we have more anomalous stars like this. But for now, with the TESS CBZ catalog, these 30 stars is all that we have for at this moment.
Yes, thank you for the answer. There was another and probably last question. Please.
Hi, I'm Luis Aguilar from Mexico. Just a general comment about dynamics. Something you have to realize when they are able to pick all of these substructures, the Lindblad diagrams, energy versus angular momentum, or even more the Gaia phase spiral, that tells you right away that the galaxy has been with a very well-defined potential for a long because if that were not the case, you will have violent relaxation, and that will scramble the signal in all of these diagrams. So what this is telling us from the dynamic point of view is that the galaxy has been very well formed for a long, long time. And all of these substructure that is raining down are relatively minor in terms of mass. They are not really perturbing to a large extent the potential. So that's very good. In fact, the Gaia phase spiral is a very delicate dynamical structure. And the fact that we can see is that it means that even Sagittarius is a minor perturbation in terms of the overall potential of the galaxy. That's it.
Yeah, I agree.
All right. So thank you for the presentation and thank you for the questions.